This conference will now be recorded.
Okay, welcome to this lecture. Today we are going to discuss the general queuing model with Poisson distribution, meaning thereby this model will serve as a general queuing model which has the Poisson distribution, means arrival is Poisson as well as service is also Poisson, meaning thereby inter-arrival times will follow the Poisson, will follow the exponential distribution, and number of arrivals will follow the Poisson distribution. Similarly, the inter-arrival times will follow the exponential distribution, and number of serviced persons will follow the Poisson distribution. So this model is very, very important model. This is a general kind of model by which we can get the specialized and particularized models by putting certain conditions or certain riders on this model. Therefore, this model seems to be the standard model for studying the queuing models in particular ways. So far, if we just go back and reminisce, remember our previous lectures, then we find that we have discussed at length the pure birth models as well as the pure death model. So now, earlier we were discussing the pure birth model as well as the pure death model separately or in isolation. Now the time has come, it has been mature to discuss the birth model as well as death model in combination. So it is no more pure birth or pure death. It is a birth and death model. So if we talk about the birth and death model, means it is no pure. So it is a birth. This will be a birth, not pure. And this will be a death. So birth, death model. Now we are going to discuss today the birth and death model. Meaning thereby we are going to discuss both in combination. Earlier in isolation, and now we are going to discuss in combination. So for general queuing model with Poisson distribution, means we are going to discuss both models, I mean in combination. What is the purpose of studying this queuing model or general queuing model with Poisson distribution? It has arrival as well as departures both. If any system has got the birth as well as death both, what does it mean? That what is the departure means what? This refers to the service obtained. So after receiving the service from the system, death takes place or the departure takes place. So if departure is taking place, meaning thereby after getting the service, departure is taking place. So how the service, how optimum, or how we can judge that service is going to be optimum? Whether this birth and death model or arrival and departure model is going to have the optimum service model or not. And therefore, if you remember here, what is this birth and death model or the arrival and departure model is just to provide the optimum service to the customers at its channel. So optimum service is very important here. This term is very important, optimum service. So purpose of the birth and death model or the arrival and death model as a general queuing model which follow the Poisson distribution is here going to be discussed for the optimum service. Now further a question arises that how we can measure, how we can judge that it is going to be optimum or not. So for this discussion, we have a very important aspect of the queuing model, that is we measure the performance of the service. Performance of the service in the system means we are going to discuss performance measure, but not this time immediately, but you can say we are going to discuss it after maturing the topic and at the appropriate time or point of time. Performance measures. This is popularly known as performance measures. It has got various terms. Performance measure. It has got various terms by the various authors. Sometimes we say that performance measure, for example, Professor Hamdi Taha just to say the performance measures. Your Kanti Swarup, literature of the Kanti Swarup says the operating characteristics. Other some management books, they say that effective measure of the effectiveness. This is known here, the PM, performance measure, the PM. One I told that operating characteristic, OC. This is also the same term used for the measurement of the performance of the system, that how to measure the performance. Another is measure of effectiveness. You look at here, MOE, same thing. So either we say that MOE, measure of effectiveness, how effective you are present here, this is not important. You are sincere, it is not important. You are very obedient, it is not important. How effective you are, that is the main purpose of any system or any person. So effectiveness, you come in the morning very timely, you go in the evening very timely, you so your demeanor or your personality traits are very fine, but you are not effective. It does not make any sense for the system because you are not contributing to the system. So if you are effective means active with, I mean with your honing skills. If you are active with your honing skills, then and only then you will give a good performance to the system. And therefore, these are the decision science terms related to decision sciences. Sometimes we call it MOU, measure of effectiveness. Sometimes we call it performance measure. Sometimes in mathematical terms we call it operating characteristics, because characteristics of the system is well known, that how to measure them. And therefore, so these performance measures will be discussed at appropriate time of the appropriate point of the time when the case has got some mature level, then we will discuss these performance measures. So we are overlooking this time this very concept. So what is the main purpose of this discussing the general distribution of the queuing model? This general queuing model, which we are going to discuss, we are absolutely going to discuss the derivation of PN. PN also at one of the point of the time or another, we have just explained it that it is a main or pivotal element of the discussion. It is in the center stage of the discussion throughout the queuing theory, and therefore the here also main purpose of discussing this model is we are going to have the derivation and analytical discussion of the PN. Why we are going to discuss the PN? PN is going to be used in the analysis, in the development of the performance measure of the queuing model. Everywhere, if you derive any formula, that formula gives us the performance measures. You have seen number of formulas, you will see, you will look at, and you will be very happy to see that how it is going to measure the performance of the queuing model. So purpose is that this time we are going to discuss and analyze, having the analytical and mathematical discussion of the PN. So PN is what? PN is going to be used for the analysis, for the development of the performance measure of the system. Please look here, performance measure of the system. And in this way, this expression of PN is going to be used and discuss the performance measure, but main purpose is what? To have the derivation of PN and its analytical behavior we are going to discuss right now. After having the discussion over of the PN, then we will discuss the performance measure. Then you will understand the role of the PN also. Now, for this, if you reminisce or revisit your previous knowledge or previous lecture, here this point is also very important. The so far studied are two important and useful states, if you remember. One was the transient state, that is also popularly known as warm-up stage, warm-up state, and another is the steady state, that is known the state of equilibrium or stability. So under these two states, which one state will play very important role in the discussion of PN? We are just moving around the discussion of PN. If you just have the note about this, this will be very interesting and fascinating for discussion. So we have so far two states. So the one is the warm-up state and another is the steady state. But as I told you that the warm-up state or the transient state involves the complexity, analytical complexity in the getting or obtaining the solution, and therefore we ignore the transient state because of one reason. Second reason is that why we ignore the transient state. Second reason is that very simple reason that most of these situations of the formation of Q are found in steady state, not in transient state. Really, the steady state or the state of the equilibrium is obtained in most of the queuing system or the queuing problems, and therefore here also we prefer to apply the steady state, not the transient state. So you must know the reasons why we do not go for the transient state analysis of PN. We go only for the steady state of the analysis of PN because of two simple reasons. That one is the analytical and mathematical complexity of PN, and second, most of the situations of the queues are found in the steady state. So we prefer the steady state here, and we will discuss the PN under the steady state. What does it mean? It means that we are free from the time variable t. We are not going to discuss the t as we have seen in previous cases we discussed, we found the derivative, but here we are going to discuss the case when the probability of the arrivals as well as the probability of departure both is not dependent on t. It is simply dependent on n. You keep in the mind. Also here it is very interesting that you may say that why we are ignoring, if it is so important, the warm-up state is so important, then why we are not going to discuss. So to be very frank, at this stage of the MSc program, this is also not prescribed in your course curriculum. So it is beyond that. So only we can discuss the transient state at the research level. So now I hope that things are clear. It is nothing new. You just look here. Thus, the general model of Poisson Q assumes that arrival and departure will only depend on number of customers in the system and not on time duration. We have repeated this very point time and again. Okay. Now the question is that let now we are going to start the mathematics. So we have certain notations we are going to use. So first notation we are going to use that let n be number of customers in the system, that is in queue and in service both. If we talk about that there are n number of customers in the system, means the customers who are standing in the queue or the customers who are in the service as well. So total number of customers in the system, in the waiting as well as in the service is n. Second point is lambda n. Look here, lambda n, we discussed this already. So lambda n is what? Lambda n be arrival rate. Why then lambda n? You may ask suffix is n, lower suffix is n, because of provided n customers in the system. We provide, we assume, we are given that there are n customers in the system, and therefore we simply write lambda n, that is the rate of arrival. So after this, now say what is mu1? Similarly, mu1 is mu1. This mu1. Mu1 be the service rate provided n customers in the system. Similarly, n is the reason that there are given n numbers, n customers in the system. What is Pn? Pn be probability distribution of n customers in the system under steady state. So it is very much clear that we are going to discuss the Pn under the steady state. So now things are very much clear that we are going to discuss Pn. Discuss means mathematical and analytical discussion. Here nothing else like or any general discussion. When we talk about the we discuss, we examine. These are the terms which are used, means we are going to examine it mathematically or analytically. So what we consider more, let queuing system be in state n. Again, this state n you look at here, the state n. We have a steady state and transient state. We are again saying one another state n. You may not get confused. That is, queuing system has, what does it mean? If I say the queuing system is in state n, now it is not a transient state. Already it is in in steady state. But if somewhere somebody says that queuing system is in state n, what does it mean? It means that queuing system has n customers for service in the system. Means I say the queuing system at doctor's clinic is 100. It is in state 100. It means that clinic has 100 patients or customers for the service or for the treatment. So it is the background we have made. That background is now let us go ahead for the mathematics. So we have known the state n means there are n customers in the system. The state of queuing system, you look at here, the state of queuing system n, if it is given in the state n, then here it is allowed to move into further states. If state of the queuing system is n, or is queuing system has state n, whatever you say, there is no problem. If it is in a state n, this can move in further two states, or this can have further two transitions, you can say. Transitions means movement. What movement? If it is in n state, I say it in n state, it can move ahead in n plus 1 state, means n plus 1 state, and this can move backward in n minus 1 state. N minus 1 state. So this is n state, and n state can move further into states. One is n plus 1 state and another is n minus 1 state. And this movement is known as transitions. So n plus 1 and n minus 1. You may say that why not, sir, n plus 2 states? Here you can add n plus 2, so forth on n plus 3, so forth on. Similarly, here also n minus 2, and you can say n minus 3, so forth on. The reason is very popular. Why? One arrival. That whenever system has, how this will n plus 1? Whenever the system has one arrival, means one birth, then state will move to the n plus 1. And when system has one death has taken place, one departure has taken place, the system will move from n state to n minus 1 state. So one arrival state will move to n plus 1. one departure is state place. Not only. That is what. And who is making the speakers? There is speaker on. So we have seen the movement or the transitions from one state to another state. My question is still remains to be answered. And my question is what? I raised one question that why not states n plus 2, n plus 3, so forth, so on. Similarly, the states n minus 2, n minus 3, so forth, so on in the downward direction. In one upward direction and another is downward direction. The question, the reason is that it has, if you remember, the very popular statement, very popular assumption that exponential distribution does not allow more than one arrival and more than one departure. It is a birth and death model. In pure birth model, it has at most one arrival, insufficiently small time interval h, and it has at most single departure, insufficiently small time interval h, and therefore the two departures or more than one arrivals are not allowed because of the assumption of the exponential distribution, and therefore the movement is not possible. N plus 1 and n minus 1 movements are only possible, other movements are not possible, other transitions are not possible because of the assumptions of the exponential distribution. So I think you agreed this very point. Look at this very interesting case now, the figure of the transition, figure 1 of the transition diagram. What does this figure say? First, you look at the state n, because we have already discussed this state. This is a general state, and then we will discuss this state. Now, when we are in the state n, means system has n customers or n patients, if it is doctor's clinic, then it can move only n minus 1 and it can move only n plus 1. When there is one arrival, so here is the arrival of one customer, so arrival rate will play very important rate. So it may move if arrival comes, that is the random, arrival is random, and therefore it is lambda n. Why this is lambda n? Why this is not lambda? Because we are in the state. Given that we are in the state n, given or provided there are n customers in the system, if you just right now remember the notation we have used lambda n. I told you provided or given that we are n customers in the system, and therefore we are using lambda n here. So this arrival, this process is random, so naturally there will be some probability also here, Pn. So with this probability, this arrival rate will take place, and similarly this state will reach to n plus 1. I think you got it. Now you look at here, this lambda in 1 is okay. Now we talk about the n, I am talking about this process. Now state n minus 1 I want to move. State n minus means if any departure takes place, that departure is also random. So if departure takes place, one departure takes place, so this becomes n minus 1 state. So what is the rate of departure? The rate of departure mu n. By the same logic, this departure is mu n, and naturally, since this is not a deterministic case, this is the whole transition is the probabilistic, and therefore it corresponding Pn will be here with this mu n is taking place. So n plus 1 justified and n minus 1 is also justified. You just look another arrow. If n plus 1 has reached here, then how this can reach to n? You look at the mu n plus 1. This is the rate of service rate. And similarly, this may have the probability P n plus 1. That is understood. It is not written here. It is only the simple transition given here. And you look at this part, the previous one is n minus 1. If we want to reach, if we state, it is not in our control. Sorry, I have spoken wrongly that if you want, no, we are not going to have this thing. Okay, it is not in our control because the arrival as well as departure both are uncertain, both are random, and therefore we can't say that we are going to have one arrival, we are going to have one departure. No, it is not in our control. This is quite uncertain, quite this is random. So this is completely random phenomena. In the very beginning, we have discussed the total randomness, absolute randomness of the arrival, absolute randomness of the departure. If you remember the first or second lecture, we had discussed this very point. Now, n minus 1 state, if you get any random arrival, then this will be lambda n minus 1. So you are moving from n minus 1 state, so lambda is n minus 1 is here. N minus 1, if you are moving from n state, so mu n is here also. Okay, so I think this part is now clear at state n. Let us go just downward. Downward is what? This may be any state, may be in zero state. This is the beginning state, so we cannot overlook this part. So if it is in zero state, then what will happen? Zero state, so here we are moving to state 1. Here number of customer in the system is 1. Here number of customer in the system is 0. That is, it is going to begin. So if it is going to begin, lambda naught is the arrival rate. There is no problem given that 0 customers. So naturally it follows the notations as we have prescribed right now. So we are reaching the state 1. But from here, mu1 departure takes place with the rate. This rate is the departure rate. Naturally, this will have the probability corresponding probability P1, corresponding probability P naught. It is understood. And without that concept of the probability, uncertainty cannot be discussed and handled. And in this way, this is mu1. Look at this very point is very interesting here. Lambda naught is defined. It is okay here, but you are not getting anywhere the role of mu naught. You may ask a very simple question, sir. If lambda naught is here, then where is the mu naught? If we talk about the mu naught, then where is mu naught? Where is mu naught? Mu naught is like here, here. It must go here, mu naught. It is mu naught here. So if it is mu naught, where it is going to, what would be state? Already it is zero state. Zero means zero customers. So at zero customers, how the departure can take place? If it has zero customers or no customers in the system, then how departure or death can take place? Or is this point justified? It seems to be justified that it is in state zero, and we can say that one departure is zero departure is taking place. What is meaning of defining the zero departure? Means any departure cannot take place here. And if you say by your saying, if I accept this very point, I admit this very point, then you will say, sir, moving it where? It is moving where? It is moving in state -1, because after zero downward is only -1. So is -1 state is defined? It is not defined. -1 customers in the system is no and never defined, because the counting process stops at zero. It does not allow the -1. We never said -1 guest has come, or -1 customer has come, -1 pencil I have given to somebody, or -1 laptop I have given somebody. No, it has no any counting sense. And therefore the mu naught is not defined. This is very important here to look at this very point. Lambda naught is defined, but mu naught is not defined. This important issue is here. Now let us discuss this very issue. Mu naught is not defined, it is clear. So for your clarity, I have this transition. You have got the graph, and this transition is what? Now you just look at here. This is the state. This is also state. This is arrival rate. This is service rate. When we move from 0 to state 1, this is lambda naught. The service rate is not defined. When we move from 1 to 0 state, this is reverse from downside. Then this is lambda is not defined here. Arrival is no need, because this is a departure. It is moving from 1 to 0. It was moving from 0 to 1. Then mu1 is defined here. And this is not defined because this is a departure. Similarly, 1 to 1 is state 1 to state 2, the lambda 1 is defined. Since it is moving, one arrival has taken place. Therefore, arrival rate is defined and the service rate is not defined. Similarly, 2 to 1. Similarly, 2 to 1. And in this very case, here arrival rate is defined and arrival rate is not defined because departure is going to take place. Here the service rate is defined, that is the. In this way, we can define anyway. We can define from 1 to 2, from 2 to 3, from 3 to 4, so on, from n minus 1 to n, from n to n plus 1, and after departure, after arrival. So the this is the transition, and in this way, today we have developed the whole process of the transition. Now, on the next turn, we will discuss. You look at here the figure once more. You look at here. If it is a state n, the how many the into what is this? Is the flow of customers. So there are two types of flow of customers. One flow of customers take place into the state. You just note this very point, be mindful of my discussion, this important discussion. There are two kinds of flow of customers. One flow of customers is going into the state, and one flow is going outside the state. So in the state or into the state and outside the state. So if we talk about the n state, what are the into flow of customers are flow into the state? This is flow into the state. This one is into, this one is into, another is into where? Another into this is into. So two flows are into. One is this one and another is this one. What are the flows outside? Which is going outside? You look at, this is outside flow. This one is outside flow and another is, this is out. There are also two flows which are outside the state n. So now we will discuss the steady state, equilibrium state, that what should be the average flow into the state and average flow outside the state under the equilibrium state or the steady state. But here there is no average. Here is a concept of expected rate of flow. Expected rate of flow of customers into the state and outside the state, because this is a random process. Therefore average is discussed in case of randomness, by the term expected. So further mathematics will take place in next lecture. So tomorrow we will discuss again. So if you have any questions, you can have with me.